Okay, so last class we did this check for understanding where I asked what is a derivative in the context of calculus, how is it related to distance, velocity, and acceleration. This term derivative means the slope or a function that represents the instantaneous slopes of a previous function. So gradient function or slope function, right? Slope function. Okay. And if we take a look just at, for example, these graphs below that we did down here, what we see is that this graph is changing at a certain rate of change. And if this is meters per second, the slopes of this graph would be velocity, meters per second. And we see that I can calculate that by basically picking 2 points infinitely close to one another, drawing a line between them, and then finding the slope of that line. That line, as I bring those 2 points together, becomes a tangent line. And so I can say that they're basically just touching the graph at one point. We notice down here in our graph that I will have a horizontal tangent line at the minimum. So there would be a 0. The rate of change, the rate that the graph is changing is 0. So in the velocity graph, that would be 0 here. And we notice here that these are negative slopes. And I'm just going to pick, like, maybe arbitrarily, that's maybe -6, -4, -2, like this. 2, 4, 6, like the slopes as I'm going up. So my graph looks something like this. Now, I know calculus, so I know what the answer is going to be already, but we see this happening. Now, the rates of change are negative. The rates of change are positive here. Negative, positive, decreasing function, increasing function. Also notice this function is strictly increasing. It's only positive, and I see a constant rate of change of up to over 1. So the acceleration is a horizontal graph, constant acceleration. So that's how this is tied together, right? The rates of change here I can graph as this function, this velocity function, would be the gradient or the slope function of the distance graph. This graph of acceleration is the derivative function or the gradient function of the velocity graph, meters per second, change of y over change in x. So what's the difference between average and instantaneous rate of change? Average means I would pick 2 points that are on the graph, and I would find the slope between them. That would be the average. I would pick the endpoints of an interval and take the average, find the slope. Instantaneous rates of change, basically those 2 points become the same point. What is the speed or the velocity at an exact moment? How is the graph changing at an exact moment? So formal definition, I've posted a picture of these solutions on WeChat, but I just said a derivative is a function that describes all of the instantaneous rates of change of another function. For example, if f of x is distance versus time, the derivative f prime of x function represents the velocity versus time of that object. The derivative of the velocity graph, f double prime of x, is acceleration versus time. And here the average rate of change finds the average slope over an interval by taking the endpoints of the interval and finding the slope between them, the secant line slope. Instantaneous rate of change is the slope at a single point, the slope of a tangent line where I bring those 2 points infinitely close together. Okay, so you can take a look at that. The solutions are posted on Moodle, not on Moodle, on WeChat. The first task that I want you to do is you have this a packet, a set of cards, and they're labeled as f of x. So I have f of x and f prime of x. F of x represents like distance versus time. F prime of x represents the gradient function, velocity function, the rate of change of this graph. And I want you to try to match them up. When you're done, there is, anyway, I've described in the video, so you'll see some solutions. So you can pause it here and do this activity. Okay, so as you were looking at this sorting piece, you were probably a little overwhelmed trying to understand how it all fits together, but you probably noticed some awesome trends, okay? So, for example, you saw some parabolas, okay? So, where's our easy parabola? So this is like x squared, and you probably noticed that all of the x squareds have a constant rate of change that's going to be a line. So this graph might be something like some x graph, okay? That goes with that. And we see that because here the function is decreasing, so the slopes are negative, negative, negative. The slope is 0 here, and then positive, positive, positive. So I see negative value for velocity, 0 positive values. Likewise, in this function, I don't know, this is something like x minus 2 squared minus 5 or something like that. We saw, I don't know, 2x, and then minus some value that's going to be down there, okay, 4. Okay, so we see also a linear function, but we see here, because this is the 0 value, it's going to cross right below at 0. You probably also noticed, where's our cubic? Oh, this one too, right? But this one goes from positive slopes, 0 to negative slopes. So above x-axis, below x-axis. And this might be something like negative x squared plus 5, and this is like negative 2x. Okay? Where's our cubics? So this is like something like x cubed. And that's not exactly x cubed, but x cubed plus blah, 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 something like that. And we see a parabola, right? 3x squared plus something. Okay? Here, what type of function is this?
The 4 one.
X to the 4th degree, and this is a...
X to the third.
Sorry, 4x, okay, 4x cubed. It's okay, it's a cubic function. Don't worry too much about that, okay? As we're exploring and understanding these relationships, we're obviously going to begin seeing some rules, and we won't have to do things the long way overall, because we start to see every time the function is going to look in a certain way. But it still tells me so much about the function, right? Here, if I see this as positive, it tells me the function is increasing, and here the function is decreasing. Does that make sense? It's also pretty profound because it tells me when the derivative function is equal to 0, that's going to be a maximum or a minimum for the function itself, right? Here I saw a minimum value, and I have a 0 going from negative to positive. Here I saw a local maximum, and I see it's going from positive to negative. Tells me maximum, okay? So we're just exploring this idea because as we look at the algebra piece of all of this, now we have some sort of context that we visually kind of see these relationships. Okay? Sound good? I need your notebooks out, please. Okay, we're formalizing our understanding of calculus. So, if I want to find the average rate of change in an area, I can take 2 points close to one another, and I can say, for example, we said last time, I think we did talk about this, if I wanted to find a slope at 3, the instantaneous rate of change at 3, I might choose the point 3 here and 3.01, right, where I have some small distance of 0.01 close to it, okay? And then I'm going to get an approximation for what that rate of change or that slope is at 3. Does that conceptually make sense? Okay? So, if I took a look at this function f of x equals 2x minus 4, what would I expect the slope to be? What's the rate of change of this graph? 2. Okay, so we already know what the answer is I'm looking for. I can basically just take the slope of this, right? The slope between those 2 points. In general, m, slope of a secant line, secant means intersecting in 2 places, I'm going to take f of x plus h minus f of x over h. And just remember this is y2 minus y1 over x2 minus x1, or the change in x. And over here, I would say I choose some x value and some value close to that, such that I have some sort of small difference for x. So I would have the order here, x plus h, f of x plus h. And over here, this would be the point x, f of x. So I would just take change in y over change in x. I can find a slope. You feel okay with that? Okay. Once I've established this, now I can find this secant line by just plugging in this. So everywhere I see x are replaced with x plus h. So I have 2 x plus h minus 4 minus 2x plus h. Sorry, minus 2 of x. Minus 4 over h. Okay, does that make sense? This is f of x plus h minus f of x over h. Just finding the slope. No?
Can you say that one more time?
Yeah. Okay. So, if I want to find the slope at, say, x, well, I need 2 points to be able to find slope, not 1 point. So I might pick a point close by, okay? When I say close by, it might be 3 and 3.01 or 3 and 3.001. Just a point that's close, where h is small. And I'm just going to take change in y over change in x. Okay, slope, right? And is equal to change in y over change in x. So in this context, in general, this would be x, and this would be x plus h, some small, tiny
Oh,
bit,
I get
okay?
what you're saying now. Okay.
So then this would be x and f of x, the y value would be f of x.
And you add h as well?
If this is x plus h, the y value would be f of x plus h.
Okay. Yeah,
Okay,
I see
so
it now.
I'm just taking change in y over change in x. This technically would be x plus h minus x, which just becomes h. Okay? this, m would be equal to 2x plus 2h minus 4 minus 2x plus 4. It's important to remember that I have a parentheses around this second function, because I'm subtracting the entire function here. When I do that, over h, notice here that minus 4 plus 4, 2x, negative 2x cancel, and I'm just left with 2h over h, and I get out 2. Does that feel pretty good? What this means is that this, so I canceled, so the slope would be 2. Okay? Notice that in this is a line, so a secant line is going to be always 2, right? Any line that I draw is just going to be the line itself. Okay? That tells me that anywhere that I check on this function, slope will be 2. That's not going to be true for this function, is it? The slope is constantly changing. But I might be able to create a function that tells me what the slope is at any point. Make sense?
And that's your function there? Or
Well,
that's
let's
just
do a second problem.
That's
Okay.
the secant line.
Yeah, we're finding the secant line first. Okay?
And also another question I have is like, so you were like, okay, from s to the distance x plus h, like that's where I'll find my slope. But like, how do you determine where between what points you should?
Because we're going to bring that infinitely close to 0 in a second.
Okay.
So we're not arbitrarily setting h. We're saying h is some distance away, and then
Okay.
we're going to make that distance 0.
Okay.
Make sense?
Yeah.
Okay. So let's do the second one. The second one's harder. And I don't know if we can still see this on the video if I turn this out. Do you think I'm going to be able to see it? If I mute this? What do you think? Can we see it okay? Yeah, totally. Okay. So here, if I want to know the slope, and I can say f of x, and I want to know the slope of this function, I'm going to do the same thing. I'm going to pick a point that's close to that. So my parabola, this is part of the parabola intersecting here at 1, something like that. And I'm picking 2 points. So I'm going to call this x plus h. Okay. So m of the secant is going to be equal to this. So I can say for this function, 3, everywhere I see x, I'll replace with x plus h minus f of x. X is some value, some x value. So if I want to know the slope at 3, x would be 3. And then maybe I pick 3.01, something close by. Okay? So to find the slope of that line or the rate of change approximately on the graph, notice these don't appear very close to one another. And you see it's not actually the rate of change of the function, but it might give me some estimate the closer I bring those points. Okay? So I could just plug in right here, but I should simplify this expression first. So this just becomes 3x squared plus 2xh plus h squared.
Wait, this is given, like this is if you don't know what h is, right?
H is basically 0. But let's say for a second that h is not quite 0. Let's say it's 0.01 or something like this.
Then you plug in h to.
Yeah, we'll plug in h in a second.
Oh, okay,
Like,
okay.
Okay, so we're finding an expression, an
Yeah,
equation
okay.
that represents the secant lines, or 2 points really close to one another on the function. So notice I have some things that are going to cancel, this and this, 5x and this, and did I forget a 1 up here? I did, right? I forgot that 1. So there should be a plus 1 in here. So that's going to cancel with this. Okay? Notice everything that remains has an h in it. So I'm going to divide out that h. So I have 6x plus 3h plus 5. This represents my function. So this is m of the secant line. Okay. So I can evaluate. If I want to know at 3, I could plug in, is this a 5? Is that right? Yeah. 5, yes. Okay. So if I want to evaluate at 3, I would just plug in 3 here. Okay? And then whatever my h is, maybe h is 0.01, something like this. Okay? And this might tell me that value. Well, theoretically, what I want to do is I don't want the secant line. I want a tangent line. I want those points to basically be the same point. So what I can do is I can take the limit as h goes to 0 of 6x plus 3h plus 5. Now pause for a second. What this means is that I'm going to bring h infinitely close to 0, but it's not equal to 0. But it's basically 0. Does that make sense? Okay. It's so close to 0 that when I evaluate this I can just say goes to 0. It's so negligible, it's basically 0. So what that tells me is that this represents the slopes of the tangent lines. This is the instantaneous rates of change. What do we call instantaneous rates of change? F prime of x. Okay, so these are the slopes of the tangents. This is the derivative function. It's also called the gradient function or slope function. Okay. And notice, if I had put that limit here, could I have evaluated it at this stage? Why not? If I said the limit as h goes to 0, could I have evaluated that limit? Could I just plug in 0? Because it's over 0. So I have to simplify it first, and then once I get an h out of the denominator, then I can evaluate the expression. Okay? When I do this process and take the limit, so I can say f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x over h. This is called the definition of derivative. And like we foreshadowed, we're not going to use this every time we want to find the derivative of a function. Okay? We see patterns and we can start using those patterns to find a derivative. But this is conceptually what we're doing. And IB will ask us to find the derivative from, quote, first principles. This is what they want us to do. So from first principles. Okay? Quote. Okay? Are you guys writing this in your notes? I see some people sleeping. Okay? Yes?
Is that prime thing, is that for 1 point?
No. So in this case, if I wanted to find out 1 point, so if I said, what is f prime of 3, this would be saying, what is the slope at 3 of the original function? Oh, I would plug in 3, right? So I get 1823.
Like, it's chill once you get that equation, but the process of getting that equation,
We haven't even done that even once yet. We're going to practice some.
Oh, okay.
Jeez. Okay, so here, so this means the slope at x equals 3 of f of x, of the function f of x.
Wait, is this like pre-algebra is to algebra as this is to calculus?
This is calculus.
Ah, okay.
So this is half of all of calculus. Can you guys believe that? Finding the slope of curves. That is half of calculus. Right there. Differential calculus. You know what the second half of calculus is called? Anti-derivatives. Anti-differentiation. Or integration. And we're going to find that we're simply going backwards. Okay? And we're going to talk about that next semester, actually. But this is conceptually half of all of calculus. Now, there's lots of applications and things like that we'll study, but this is not so difficult. Slope. Slope. Okay? Now, some notations we're going to see. We often see f prime of x. Okay? But we might also see things that look like this. I'm just going to slide that here. We might also see dy over dx. Now, this comes from delta y over delta x. Right? Does that feel pretty comfortable? Dy dx. We have different notations because of different inventions of calculus, but that's coming next class. Okay? Leibniz versus Newton. Okay? So dy over dx, f prime of x. I also might see this, d dx of y. So I'm taking the derivative of this. And notice it's just the same equation up above, but I've pulled out the y, so I'm taking the derivative of y.
Wait, what's
So all those three are the same.
They mean the exact same thing. I might also see d dx of something, of f of x or some function. I might see y prime. These are the exact same thing, but typically if something is presented like this, I give my answer like this. Does that make sense?
Yes.
Okay, but they all mean the same thing.
And what does the D stand for?
Delta, like this.
Like difference.
Yeah, difference, but it's like the infinite difference as I bring them closer and closer together. Okay? Alright. You ready to try some problems? Yes? Is that what I heard?
Can we try try them as a group.
You guys are gonna love this. You're gonna love it.
What's the real world application other than cars?
I can't even begin to open that can. There's an infinite number. Okay? Okay? Alright? Are you ready? I want to hint also that when you're thinking about your internal assessment next year, calculus is a really rich topic to use.
Wait, we have one of those for math as well.
We have to write like an essay on it.
For math?
Yes.
Oh.
Yes. You have an IA for math. Next year.
And it's not a test. It's like a
Every subject. Okay. Okay, you guys are going crazy.
guys, we're filming. Guys.
We're filming. Okay. Hey, focus. We have 20 minutes. Okay. Ready? Okay. Let's find the derivative of this function from first principles. I'll do it with you, and then you guys get to try these ones, okay? So, first, some of you are already saying, Susan's already saying, it's not x squared. Okay, nice observation. Let's show or find the function, the gradient function that describes the rates of change of that function, okay? So, I'm going to take the limit, and you probably want to, you can do it there, that's fine. Okay, limit as h goes to 0 of f of x plus h minus f of x. I want every single person actively doing this with me. Yeah, there it is. This is the derivative, right? If I want to find f prime of x, I take 2 points very close to one another. And then I'm going to bring those points infinitely close. So, 3x plus h cubed plus 2 minus f of x. Notice my parentheses. Over h.
Wait, where's the cube?
Because it's cubed. Okay? You're already thinking, yes, binomial expansions. Okay. Yeah, it's cubed. That's an easy one. Okay, so I'm going to say here, the limit as h goes to 0 of 3 times x cubed plus 3x squared h plus 3x h squared plus h cubed plus 2 minus 3x cubed minus 2 over h. Yeah. You guys remember those binomial expansions?
Yes. No.
Oh, they're so great. Where's my Pascal? It's right here. Okay. All right. Let me just multiply in that so we see what terms cancel. So I have 3x cubed plus 9x squared h plus 9x h squared plus 3h cubed. Okay. Feeling okay?
No.
This is so cool. Okay, what cancels? This and this.
Okay.
Okay. Okay, I can factor out an h. Okay. Now that I want to evaluate that limit, what can I do? No problem with plugging in 0 now, right, for h? So, f prime of x is equal to 9x squared. Okay? F prime of x is the slope function, gradient function. It tells me the instantaneous rates of change of this graph. Cubic, quadratic. Okay? If I wanted to know the slope at x equals 1, it would be 9, right? So if this was distance, this would be the rate of change in meters per second at that time. Is it making sense?
Not really.
No? Oh my gosh. This is beautiful. We only have to do this very rarely in calculus, okay?
Wait, do what part?
This
Oh,
process, okay? Pretty much only today, and maybe on a quiz in the future, okay? Now, IB will ask you occasionally, or there's potential they're going to ask you to derive derive from first principles, but usually not. Okay? So this helps us to build our conceptual model. What are we doing? Finding the slope between infinitely close points. That's like algebra 1,
Yes.
right?
But is this like the hard part after this video?
I would say it's all pretty intuitive. Yeah.
Like if you get it, you get it. If you don't, you don't.
No, I didn't say that. I said we'll find that it's pretty intuitive. It's just the more we explore, I think the more it's going to make sense. Okay, so don't. You're scared because you've never studied it before, but that doesn't make it a bad thing, right? Okay. All right. Can you guys try to find the rest? This one, let's multiply them out first. 2x squared plus 2x. This one's going to be 9x squared minus 24x plus 16. Okay? You can work together, but I want you to see if you can derive from first principles the slope equation. Hold on. If you saw this, the square root of 2 plus 5, and you wanted to get rid of this in the denominator, what would you do?
Oh.
Rationalize by multiplying by the...
The constitute.
Oh.
Thank you, the conjugate. So you would multiply
Did you just say
by...
constitute?
Okay, so the same thing is true here, but I'm going to go backwards. It feels weird because I'm going to put the square root now in the denominator. But what that's going to allow me to do is, notice x1, it's going to cancel and I'll be left with h on top. So I'll multiply by a form of 1, the conjugate with a plus in between.
I got it.
So what's the numerator going to be?
Word.
X plus h plus 1 minus x minus 1. Divided by h, and then that business. Okay? I see that this is going to cancel. Okay? The x's are going to cancel. I'm just left with h. So I can cancel this h down here. Okay? If I want to evaluate that limit, can I plug in 0 for h now?
Yes.
Yes. When I do that, I get, so that just goes to 0. I get root x plus 1, root x plus 1. So f prime of x is equal to 1 over 2 x plus 1. Okay, this one was 4x plus 5. Derivative of 5. What should be the derivative of 5? 0. How do I know f prime of x is going to be 0 there?
There's no, it's a
What does the graph
horizontal
look like?
line.